Hi grade 12s and welcome to this video. In this video, we will be working on the Euclidean geometry section of the Mathematics Paper 2 for November 2025. Okay, just keep in mind that this is the Euclid section, so in questions 9, 10, and 11, we need to ensure that we give reasons for our statements. Okay, so looking at question 9. Question 9.1 says, in the diagram, O is the center of the circle, K, T, and P lie on the circle. And so they want us to use the diagram above to prove the theorem which states that the angle subtended by a chord or arc at the center of the circle is twice the angle subtended by the same chord or arc at the circumference. So that is, of course, proof that angle TOP is twice angle TKP. Okay, so this is a common proof that they asked for. So with this one, what we're going to do is we're going to draw a radius from K to O first, and we're going to extend it. Extend it to a point, and let's just say we're extending it to a point, and we'll call that point Q, seeing that P is here. I was going to call it P, but P is already there. Okay, and then once you do that, we are going to go ahead and just name these angles. So this is now angle K1 and angle K2, and that's angle O1 and angle O2. Just make sure to write down any constructions you have made, so also just write that down. Okay, now to prove this theorem, what we're going to use is the individual triangles that we see here. So we have this triangle KTO, and you see that this triangle has an exterior angle. So that is this angle, angle O1. What do you know about the exterior angle of a triangle? It is equal to the sum of the two opposite interior angles. So this plus this angle gives you angle O1. So we'll start with that. We'll tell them that angle O1 is equal to angle K1 plus angle T, and that is because we have the exterior angle of a triangle. Okay, now see what we can also see about this same triangle. Do you see that this triangle, look at the sides it has. From O to T, that is a radius, okay, from the center to the circumference. Again, from O to K, that is also a radius. So these are equal because they are equal radii. The radius is the same all through, okay, from the center to the circumference. So go ahead and state that. Tell them that KO is equal to TO. And this is because we have equal radii. You can just tell them radii. And now look at what we can do with that. If these are equal in length, then it means that the angles opposite their equal sides are also equal because we have an isosceles triangle here. So it means that the angle opposite that side, that is angle T, and that side, that is angle K1, they are equal in length. So go ahead and tell them that this means that angle K1 is actually equal to angle T because we have angles opposite equal sides. Okay, and now that we know these two angles are equal, we can actually update this equation. So it means that angle O1 is actually equal to, since these two are equal, it's actually equal to angle K1 plus, but angle T is equal to angle K1 as well, so plus angle K1. And so this means angle O1 is equal to 2 angle K1. Now you're probably wondering why we're focusing on angle K1. The reason why is because they asked us to prove that the center angle, okay, the angle at the center is equal to twice the size of the angle at the circumference. Do you see that angle K1 is part of the angle at the circumference? So that's why we are focusing on that angle. Okay, so that is our conclusion over there. And then we are done with that part of that circle. Now, looking at the second part, again, we have the same situation here. We have a triangle with an exterior angle. So that exterior angle, angle O2, we'll just tell them angle O2 is equal to, and so that would be equal to the sum of the two opposite interior angles. Okay, so it's angle K2 plus angle P. So we'll add these two angles together and tell them angle K2 plus angle P and put down your reason. Okay, it's same thing all through. So we're just going to copy and paste that. And then you're going to see the exact same situation going on here as well. Again, in this triangle that we have, okay, with the blue markers, do you see that this KO, okay, is a radius? This OP is also a radius, so they are equal in length. So tell them that KO is equal to PO, and because they are equal radii, so they are equal. And because they are equal, it means the angles opposite their equal sides are also equal. So you can see that angle K2 would be equal to angle P. Okay, so we'll put that down. Tell them that angle K2 is equal to angle P. And now we can update this equation. So angle O2 is equal to angle K2 plus, and we know that angle P is also equal to angle K2, so plus angle K2. And so this means angle O2 is equal to 2 angle K2. Again, don't forget the reason here. The reason they're equal is because we have angles opposite equal sides. Okay, so now we have our two main equations, okay? We have that angle O1 is equal to 2 angle K1 and angle O2 is equal to 2 angle K2. And here is how they come together. You see, what they asked us to prove is that angle TOP, which is the angle at the center. And do you see how that is made up of angle O1 and angle O2, which we just found, okay? We just found these. And so we're going to add them together to form that angle. So therefore, angle O1 plus angle O2, and what are they equal to? Well, we know that angle O1 is equal to 2 angle K1, so 2 angle K1 plus, and angle O2 is equal to 2 angle K2. And so look at what we have. These two added together, do you see how they form this angle at the center, TOP, that they were referring to? So we're going to say that that is angle TOP. And then look at what we have here. Notice how you have a 2 and a 2. We could just take 2 out as a common factor just so that we can separate those k's. Okay, so now if you open a bracket, look at what is left. Angle K1 would be left in the first term. Okay, if you say this divided by that, common factor. And then again, this divided by that, you get plus angle K2. And what does the sum of angle K1 and K2 give us? You see that if you add those angles together, they give us this angle they refer to, TKP. And so, finally, this concludes that angle TOP is indeed equal to 2 angle TKP. And there we go, we have proven this. And that is it for that question, and moving on to the next question. Okay, we are now on question 9.2, which says, in the diagram, O is the center of the circle. POF is the diameter of the circle, and MF is a tangent to the circle at F. Okay, so you see what they're doing there. O to F, radius, okay? There's a tangent. Remember the relationship between a radius and a tangent at their point of contact. Okay, and then they tell us that OM cuts the circle at L, as we can see. And angle P is equal to 32 degrees. Okay, the first question, calculate with reasons the size of angle O2. Angle O2 is the angle at the center. Okay, grade 12s, they always follow this flow. Grade 12 and grade 11. I've noticed that whatever proof they asked you for, the next question would usually have to do with that theorem, okay, which you had to prove. So as you can see, they want angle O2, the angle at the center, subtended by arc LF. And so this is going to be twice the size of the angle at the circumference, okay, subtended by that same arc. As you can see, if this is 32 degrees, this is double of it, which is 64 degrees. And so we can just tell them angle O2 is equal to 64 degrees and then give them our reason, okay? Angle at the center, you can just like copy it from the previous one, just shorthand it so it doesn't take so long to write. Okay, so there we go. And that is it for that question. Moving on to the next question. The next question asks us for angle M. Okay, so let's look at angle M. It's over here. How do we find this? You can straight away see that this is a triangle that we have. There's actually two ways to find it, okay? With this one, you have a triangle. And remember what is going on over here, okay? We have a radius, OF, and a tangent, MF. The radius and a tangent are perpendicular at their point of contact. So we immediately know we have a right angle triangle here. So we can just tell them that this angle is 90 degrees. So I'll start by saying that angle OFM is 90 degrees, or let's just call it MFO. So angle MFO in alphabetical order equals 90 degrees, and that is because we have the radius being perpendicular to the tangent. Okay, and then we can just find this angle now. So we have two other angles, and let's find the third angle there. So to find angle M, we'll just say that angle M is equal to, you know that the sum of angles in a triangle, they add up to 180 degrees. So this plus this plus this give us 180 degrees. So to find this angle, just say 180 degrees minus 64 degrees and minus the 90 degrees, and we'll get our answer. Okay, so here we are. We're going to say 180 degrees minus the 90 degrees minus the 64 degrees. And then, of course, that is 90 degrees minus 64. 90 minus 60 is 30. Minus 4 is 26. So 26 degrees is what we get for angle M. And our reason there, of course, is that we have the sum of angles in a triangle. Okay, so that is it over there. Another way you could have found this is by using angle O1, because look at what we have. We have a triangle here, and then angle O1 is created because we extended, or they extended this line. Okay, so this is the exterior angle. So you could have just said, oh, this is 90 degrees, and then we're looking for that. So if you find angle O1 using the sum of angles on a straight line, seeing that you have 64 degrees, you could have found angle O1 and then use that exterior angle to find this angle, okay? Because this plus this gives you this exterior angle. Okay, so that is another way of finding it. But that is it for that question, and we are going to move on to question 10. Okay, we are now in question 10, and question 10 says, in the diagram, PQRS is a cyclic quadrilateral. Okay, so just note those points on the circumference because that's the only part that you can consider, okay, as a cyclic quad. Okay, and then they tell us that T is a point on the circle such that QT is perpendicular to RS at V. Okay, so we have 90-degree angles over here. And then they tell us that PT and ST are drawn. There's PT and there's ST. Okay, those lines are drawn. And they also tell us that angle Q2 is equal to 35 degrees and angle R is equal to angle S1. We need to put that down. So angle R is equal to angle S1. Okay, now the first question, 10.1, says calculate with reasons the size of angle QTS. So angle Q to T to S, this angle. How do we find that? Let me just put it in a different color, so I don't get confused. Okay, let's stare at this angle and see how we can find it. So with this angle, it's made up of two parts, okay, two angles, angle T1 and angle T2. We could try to find them individually. But what I would suggest is at first look at it and then try to find it alone. To try to find it alone as an angle, just see what it is part of. So I can see it's part of the cyclic quad. Yeah, not very helpful because then there's nothing else that they gave us, except for these two being equal. But then if we don't know this one, then, how do we find it? So let's try to use it as a triangle that it's part of. Okay, so looking at that angle, okay, as a part of this triangle, do you see now that this is 90 degrees and we would just need this angle and then we have found it, okay, because then this would be the third angle in this triangle. So how do we find this angle? Okay, so it's at this little corner over here. So since it's at the circumference, you can just start looking for theorems that work with angles at the circumference. It is subtended by this arc, RT, and do you have another angle at the circumference also subtended by this arc? Yes, we do. Okay, we have this angle, which is angle Q2. It's also subtended by that same arc. Okay, so that means that this is 35 degrees. I'm just going to put that down. This is 35 degrees and we can state that down first. So tell them that angle S2 is equal to 35 degrees because we have angles at the circumference subtended by the same arc or chord, of course, but in this case it's an arc. They are equal. Or you could, of course, use the short reasoning, which would be angles in the same segment. Okay, angles in the same segment are equal. Now that we have found that, do you see that we can just use this triangle? We already know that this is 90 degrees because they told us about that, those being perpendicular. Okay, so let's just put that down. We'll go ahead and tell them that this angle we are looking for, which they call QTS, or just say QTS. To find this, we say 180 degrees minus 90 degrees minus 35 degrees. And our reason is because of the sum of angles in a triangle. And so angle QTS is equal to, that gives us 90 minus 35 is 55 degrees. Okay, so there we go. 55 degrees is our answer there, but also just make sure to put it down. This is 55 degrees, so we can just use it for anything else that we need. Okay, now moving on to the next question. Question 10.2 says, prove that PQ is parallel to SR. Okay, so proving that two lines are parallel. To do this, we would have to use theorems that relate to parallel lines. Okay, so now that we have these two lines, we're going to have to we can use fan angles. That would be the easiest, way that you could think about fan angles, because fan angles only work on parallel lines. So if these lines are parallel, then it means the alternate angles are equal. This is equal to this. Or you could also say the corresponding angles are equal. This angle is equal to this angle. Or the co-interior angles add up to 180 degrees. Okay, so let's go ahead and find fan angles using these two lines. Okay, now straight away, I can see, and we can draw an F here. So do you see that there is a backwards F? And so we know the size of this angle V4, that is 90 degrees. And so we would have to find the size of angle O1. Okay, so to find angle O1, how can we do that? Okay, so we already know this is 90 degrees, and we just need to find angle O1. So with angle O1, do you see that it lies right opposite this angle? So here's the thing about this. We have a cyclic quad. And remember, these are the points on the circumference. So this is your cyclic quad. So with this quad, because it's a cyclic quad, we know that the opposite angles of a cyclic quad are supplementary. They add up to 180 degrees. So angle O1 plus this entire angle gives us 180 degrees. So to find angle O1, we need to find this little part. So we can say this plus this gives us 180 degrees. So angle S1, remember it is marked because it's equal to angle R. And if we can just find angle R. Do you see that angle R is at the circumference and it is subtended by this arc SQ? Can you also see another angle at the circumference supported by the same arc? That will be this angle, angle T. Okay, that is subtended by SQ as well. So these are equal. And so we can go ahead and say that this is 55 degrees. And we'll put our reason down. We'll tell them that angle R is equal to this angle QTS. And they're both equal to 55 degrees. And the reason for this is because we have angles in the same segment are equal. Okay, so if this is equal to 55 degrees, from the beginning, they already told us that these two angles are equal. Angle R equals angle S1. So this would mean that this is also 55 degrees. Okay, so just tell them that. So therefore, this means that angle S1 is also equal to 55 degrees. Okay, so now here's the main point. To prove that these lines are parallel, then we can just use the co-interior angles that we can see here. Okay, you could have used corresponding angles. Yeah, that's fine. But I mean, because they have already marked this one out, I'm just going to go with co-interior angles for this. So let's find angle O1 first. We know that this is a cyclic quad. So the opposite angles of a cyclic quad, they add up to 180 degrees. So angle O1 plus this entire angle, they should give us 180 degrees. And you can already see together, this gives you 90 degrees. Okay, so we have angle O1, okay, is equal to 180 degrees minus this angle that we have. And let's just call it angle PST. Okay, so angle PST. And our reason for that is because of the opposite angles of a cyclic quad. Okay, so angle O1 is equal to 180 degrees and they sum up to 90 degrees. Therefore, angle O1 is actually equal to 90 degrees. And now to finally prove that these lines are parallel, PQ is parallel to SR, can you see that between these lines, okay, using these lines, we can create co-interior angles. So this angle, which is 90 degrees, we know that now, plus this angle, which was already 90 degrees, they add up to 180 degrees. And so it means that these two lines indeed are parallel because the co-interior angles add up to 180 degrees. Okay, so I'm just going to show them this is 90 degrees. I'll just put it like that. And let's go. So we're just telling them that if you take angle O1 plus this angle here, angle V1, that they add up to 180 degrees. Okay, so angle V1, 90 degrees plus 90 degrees. I mean, you could have just said they add up to 180 degrees. And then that will be perfectly fine. And then we can finally conclude that these two lines are parallel. So because they add up to 180 degrees, therefore, it means that PQ really is parallel to SR because the co-interior angles added up to 180 degrees. Therefore, the lines are parallel. Okay, so there we go. And that is how we find that. And that is it for that question. Moving on to the next question. And then the last question, question 10.3, says, prove that PT is a diameter of the circle. Okay, how do you prove, before even looking at PT, how do you prove that something is a diameter? How do you know that a line is a diameter? Well, you have to use a theorem that refers to a diameter. And we know a theorem like that with our circle theorems. Do you remember that if you ever have a diameter, it passes the center, of course, yes, but if you have an angle which is subtended by a diameter, okay, in a circle, that angle is going to be equal to 90 degrees. So if you find out that this is 90 degrees, then this is a diameter. Okay, so that's what we're going to look for there. So the line they're referring to is PT. So let's look at PT. And how do we show them that this is, straight away you can see. PT, why are you a diameter? Because the angle that PT subtends is a 90-degree angle, angle O1, which we previously found. Okay, so in this case, no calculation needed. You can just show them that it's a diameter because of that. So tell them that angle O1 is equal to 90 degrees. And this was already proven. Okay, in the previous question, we proved this. And so therefore, PT is a diameter. And the reason it is a diameter is really because of the converse theorem of the angle subtended by a diameter, or really the angle in a semicircle. And here's why we call it a converse. So a converse is really just like the reverse theorem. So if you are given a circle and you are told this is a diameter, I'm not asking to find or prove that it's a diameter. I'm telling you it is a diameter. So if this is a diameter, what would be the size of this angle? This angle would be equal to 90 degrees, because we know that if an angle is subtended by a diameter, as you can see, this is the diameter, the one point to the other point. This angle is subtended by that diameter. You see how if you put your finger over here and your one finger over there, and you trace back to see the angle created by that line, okay, that line coming from those 2 points, you see how it traces to angle P. And so that's why we say it subtends that angle. So with this, if I told you that this is a diameter, find this, you'd be able to say this is 90 degrees because it's subtended by a diameter. But if I gave you a circle and I didn't tell you that this was a diameter, however, I did show you that there's an angle that this line subtends, but this angle happens to be 90 degrees, then you would be able to say, oh, then that means that this is a diameter because it subtends a 90-degree angle at the circumference. Okay, so that's what I mean by that is really just the theorem in reverse. Okay, so that is our reason over there. Okay, so that would be our answer. There was no need to find anything. We already saw that and we were able to just conclude that it is a diameter, and that is just for 2 marks. Okay, so that is it for question 10. Okay, so we are on the last question for Euclid and for paper 2. And question 11.1 says, in the diagram, triangle ABC is drawn. BA is produced to E, as we can see, and F and D are points on BC. Okay, F and D on BC, such that AD is parallel to EF. And then they also tell us that AC and EF intersect at G. And now we have to put these proportions down so we don't, lose them. So they tell us that CF over FB equals 2 over 5. So CF over FB is equal to 2 over 5. So when you take the lengths of these sides and you put them over each other as CF over FB, it will simplify to 2 over 5. This does not mean that CF is 2 units and FB is 5 units. No, that's not what they're saying. They're just saying that the ratio is equal to 2 over 5 because when you divide them, they just become 2 over 5. So what we can do to ensure that we don't call this a length, okay, is instead of saying just 2 there, we're going to say 2a, okay, and then call that 5a. And so if they give us any other, as you can see, they've given us this, we will also make sure we give it a variable, just to remember that they've given us a ratio, not the actual length of those sides. Okay, and then they also tell us that CG over GA equals 3 over 2. So CG, we'll just take that and call that 3B. And then GA, I'll call that 2B. Okay, let's answer their questions. The first question says, calculate with reasons the value of FD over CF. Let's see where that is. FD over CF. Okay, this one is very simple. It's something that you already have. Do you see that we have a triangle? Okay, an upside down triangle. And you already know that AD is parallel to GF. So because these lines are parallel, we can use the proportionality theorem here. So to find FD over CF, we're just going to say FD over CF is equal to, and then look at the lines they line to, okay, horizontally. So when you look at it, FD is this over here. It lines up perfectly with GA. So is equal to GA over, and then CF, that perfectly lines to CG. Okay, so we'll just say CG. And then put down your reason. Your reason for this is because of, you can either say the proportionality theorem, or you can say it's because we have a line drawn parallel to one side of a triangle. Okay, and now finally conclude. So this means that FD over CF is equal to, okay, so we're just going to put down these ratios here. So you can say that GA is 2, okay, 2B, and then CG is 3B. So even if you had written it as 2B over 3B, because B stands for the same length, they would still cancel. So you don't really have to do that. You already know that you're working with lengths from one side of this triangle. So you're not comparing lengths from different parts of the triangle. So that is simply just 2 over 3, and that is our answer over there. Okay, moving on to the next question. Okay, another thing that I just like to do as well, just so I can keep track of these, is I'm going to put those ratios here. So this is 3, but I'm not going to call it B, because it's not part of the line with B. So I'll just call it 3C, and then I'll call that 2C. Okay, so just keep it there so we can keep track. And moving on to 11.1.2, which says we need to find BA over EA. Okay, BA over EA. EA is way over there. Let me just get rid of these because I know I want to rather use this color to focus on whatever question we're working on. Okay, so looking at BA, that is that over EA. Okay, so it's just these that they're asking for. Always just look for the triangle they are referring to here. So you can see it's this larger triangle, and then ensure that you have that one side, okay, being parallel to the third side of the triangle, which we do. This line again, but it's now this triangle. So how do we find this? To find BA over AE, do you see that you have to find the side BD over DF? And so that's what we need to focus on. Okay, so let's see how we're going to find this. So because we're trying to find BA over EA, you can see what they line to, and so what we need to focus on. These two, okay? So we need to find BD over DF. And we just need to find their ratios. And here's the reason I put these down, okay? 3B and all of those. They're going to come in handy here. So because we know these are ratios and they're not actually the length of these sides, here is what we can do. You can see that the main problem here is just trying to find BD because it's the only thing that we don't have. We don't have BD. To find BD, you can see that this full length, okay, not really the length, but the whole ratio is 5A, right? And then this little part is 2C. Of course, they're not in terms of the same variable, but we can still express BD like this. So to find BD, you can just say BD is found by taking this entire 5A and then you say minus the 2C and then we get BD. Okay, so that's what I'm going to do first. So long BD is equal to, and I'll just say 5A minus 2C. Okay, but to properly do that, we're probably going to have to just let them know that we assign these variables. So let's just go ahead and tell them that initially we just made CF equal 2A, okay, and then FB equals 5A and so on. So I'm just going to assign these and just tell them what they were equal to. Okay, with that, I see that I don't really have to focus on the ones with B because we're not really working on that. We're working on this line specifically. Everything just comes from this side. Okay, so we can just tell them, and CF is also equal to 3C. So, I mean, CF can just have two lengths, okay? But of course, they still represent the same thing because A and C are two different values. Okay, not trying to make it confusing. I'm just trying to make sure that those are there so it's not going to be confusing. We can see where that came from. But remember, we only name these like this just to show that this is not the length of the side. It's a ratio. Okay, it's the portion it gets depending on whatever the length of the actual side is. Okay, so lastly, I'll just call FD to C. Okay, so, and FD is equal to 2C. And that's what we have. So, BD would be found by saying 5A minus 2C. Remember that. Okay, so BD, that is how we find it by saying this entire 5A minus FD, which was 2C. Okay, so now with that, look at what we can do. Let me remove these for now. We have this part, which is 5A minus 2C. Okay, now the one thing we would need to work on here is to name this according to one variable. Okay, so right now it has two variables, A and C. I wanted to just have one variable. And the variable I wanted to have specifically is C because this already has C. And so if we're trying to get this over this, okay, then it is best to have two ratios that have the same variable. So we can actually put them over each other and get the simplified ratio. Okay, so the next goal, the next problem that we have is this. We need to express this better, okay? This needs to be in terms of C, not A and C. So we need to find a value for A. And so that's what we're going to do here. How do we find a value for A? Do you see anything in this diagram that can help us to find a value for A? Well, do you see that over here, CF is equal to 2A, but CF is also equal to 3C? That solves our problem. We can simply say, because we can see that CF, we already, stated that they were equal. We said that CF was equal to 2A and 3C. So CF is equal to 2A, but it's also equal to 3C. So we can just say 3C equals 2A. And what we're trying to do is find a value for A so we can put it in here. So how do we find A? By making A the subject. How do you make A the subject? By getting rid of the 2. So divide both hand sides of this equation by 2. And so A is equal to 3 over 2C. And there we go. And so what I'm going to do is take this 3 over 2C as A and put it inside the equation for BD. So this means that BD is actually equal to, and so we have 5 and there's A. In place of A, substitute 3 over 2C so that they can both be in terms of C. Okay, and then BD is just a ratio in terms of C. And then minus 2C. Okay, there are different ways of doing this. This is the way that I have used now for a while. So to multiply these, 5 has a natural denominator of 1. So we will say 5 times 3, which gives you 15. And then 1 times 2, which gives you 2. So this is 15 over 2C. Minus 2C. How do we subtract these? Okay, 15 over 2 is 7.5. So you can just say minus 2C, which would be 5.5. You can use your calculator for this. And so that is 11 over 2. So BD is actually equal to 11 over 2C. And that's what we have here for BD. Now we can finally find what they're asking us for. So instead of writing this as 5A minus 2C, just call it 11 over 2C. And now here we are. We have this in terms of C, this in terms of C. They wanted us to find BA over AE. We can easily find that now. BA lines to the 11 over 2C, and then AE lines to the 2C, okay, the FD, which is 2C. And so we're just going to say BA over AE is equal to 11 over 2 divided by 2. But of course, before saying that, we'll just start off by telling them that BA over AE is equal to, so BA over AE is equal to, and then we'll show them what it's equal to. That is equal to BD over DF. Okay, so BD over DF. And our reason for that is because of the proportionality theorem. Okay, if you have a line drawn parallel to one side of the triangle, then we can actually use those proportions like that. Okay, so there's our reason. I just copied and pasted it. And so finally, BA over AE is equal to, and remember, we already found that this side was 11 over 2C, and this is 2C. So if you put them over each other, if you like, you can call it C. It's not necessary, but you can. Okay, if you did that, 11 over 2C divided by 2C, the C's would still cancel, so it doesn't even matter. And so BH, just to ensure that you have named them in terms of the same thing because they are on the same line. Okay, so finally, what is 11 over 2 divided by 2? You know that if you divide using a calculator or, by head, it is going to be 11 over 4 because you're saying 11 over 2 divided by 2. So use tip and times. This becomes multiplied by 1 over 2, which is 11 over 4. And that is our answer. Okay, and that is it for that question. Moving on to the next question. Okay, we are on question 11.1.3, which is actually a question I left out. I forgot. I didn't realize that I left it out until I started editing. Okay, so here it is. We have to find the area of triangle GCF over the area of, and this is not a triangle, clearly. They say GFDA. Okay, so let's pin this and see what they're referring to. Okay, so triangle GCF, that is this triangle here that we have, GCF. And then we have this, it's a quad, some sort of quad. We have GFDA. So that's from G to F to D to A. So this is what we have. Okay. Okay, so do you see that what we can do is just take the area of this big triangle. And then if you say minus the area of this small triangle, then we're going to be left with this area. Okay, so the area of the trapezium they were referring to. Okay, so let's go ahead and do that. Okay, so this is what we have. And the area of triangle GCF, that one is not a problem. We can simply find this by using, as you can see, we don't have any clear perpendicular height. Normally to find the area of a triangle, if you're given a height, you just say a half multiplied by its base, multiplied by its perpendicular height. But in this case, okay, in none of these triangles, we're not really given a height. So what we're going to just do is we're going to use the other area of a triangle, the one that doesn't require you to have a perpendicular height. And so that would be this situation. You have this triangle, let's say it's called ABC. You're just going to say a half multiplied by this side, AB, multiplied by this side, BC, and then sine of that center angle, angle B. So it just depends on whatever angle you have available. Now, in this case, we don't have an angle available, but there is a relationship between that quad and really just the triangle and a particular angle. So do you see that we have angle C here? Angle C is part of this triangle that we need to find the area of that triangle. And it's also a part of this bigger triangle, which we are going to use to find the area of that trapezium. So in that case, that's the reason we're using that formula. Okay, so I'm saying that this is equal to, we still have the area of triangle GCF, but then now I'm showing that to form this triangle, we simply just say the area of this larger triangle, okay, triangle CDA minus the area of this triangle on top. Okay, if you take the area of that little triangle, triangle GCF, then you end up with the area of that trapezium, okay, over there. So this is equal to, and we're just going to now find them. So the area of this triangle on top, we are going to take the side, so we'll say a half multiplied by this side, and that's going to be the 3. I won't say 3b, it's not necessary, because we're also going to have something with b, okay, in the denominator. Okay, so multiply by, and then the other side of it. So in this case, because I'm using this larger triangle, okay, to find the area of this trapezium over here, what I'm going to do is use the ratio of c. Okay, so I am sticking with one variable for one line. Okay, so a half multiplied by, and then I have to say multiply by 3. So that's 3c. Okay, and then multiply by sine of angle. The common angle is angle C. And so that's sorted out for that area of the triangle on top there. And then the area of triangle CDA, we'll just say a half multiplied by, this is this bigger triangle here. And we'll say a half multiplied by its side, which is 3b and 2b, which gives us 5b, but I'll just call it 5 because you see with that b on top, they would cancel once we simplify. So 5 multiplied by, and then this side, which is going to be 3c and 2c, which is also 5. So 5c, which I'll just call 5. And then sine angle C. That is also the common angle there. And then minus, we have the area of triangle GCF. So GCF is this one on top. We can just rewrite it. That is a half multiplied by 3 times 3 sine of angle C. And so you can see how this would just simplify. So in the numerator, if you say 3 times 3, you get 9. And a half of 9, that is just 9 over 2. We'll just say 9 over 2 sine angle C. That's what we have there. All over. And then here, 5 times 5 is 25 times a half is 25 over 2 sine angle C. Minus, we know this becomes 9 over 2 sine angle C. And so this is equal to, again, 9 over 2 sine angle C all over and then subtract here. So that would give us 25 minus 9 is 16. So 16 over 2 gives us 8. 8 sine angle C. And you see now that sine angle C and sine angle C cancels. And all we are just saying is 9 over 2 divided by 8. Okay, so you can say multiply by 1 over 8 or use your calculator. And so this would give you 9 over, and that is 16. Okay, so that is our answer. Our final answer is 9 over 16. Okay, so that is it for that question. And moving on to the next question. Okay, so now we are on 11.2, the last sections of Euclid, which is usually the most challenging one. So let's get into it. We have 11.2 and it says, in the diagram, WVZR is a cyclic chord. So this is our cyclic chord, as you can see there. Okay, they also tell us that RZ is produced to Q, and then a tangent is drawn from Q to touch the circle at S. WV is produced to E, a point on ZQ, and then RW produce meets, okay, these are just produce. We're just looking at all these. I'm looking for special things like tangents, parallel lines. We can see them already. And then PQ is parallel to WE. Okay, so keep that in mind. And then they also tell us that RS and ZS are drawn. Okay, so those are just lines. RS and ZS. Okay, so special things that we have a tangent, okay, to the circle at S, and we have parallel lines, and we also have a cyclic chord. So this is one of those ones where they don't, unfortunately, give you angles, okay, the actual sizes of the angles. So you need to be really careful here. Make sure to use highlighters and mark things out as you find them. So the first question says, prove with reasons that 11.2.1 PR, and immediately I see this, I will start highlighting. Where's PR? PR is this line over here. PR is equal to PW, okay, this is PW, and then multiply by QR. Where's QR? Okay, that longer line, so let's just mark it in purple as well. QR, and then over QE. Okay, QE. Okay, this one easy. This one is not a problem because it's working with the theorem we just used previously, which is the proportionality theorem. Okay, do you see how you have these parallel lines and then this big triangle? So you know that using the proportionality theorem, you know that QE, okay, over QR would be equal to PW over PR. So let's go ahead and state that and then just make PR the subject of that equation. Okay, so we'll just tell them, I can say that QE over, I don't want to put PR in the denominator because they had PR here. Okay, and if you look at PR as a fraction, it's PR over 1. So I'm not going to put that in the denominator. What I'm going to do is say PR, let's start here. PR, okay, over PW. If you take PR over PW, it is equal to, and then we'll just follow from there. So PR So you're going to take that with QR. So that's QR over QE, okay, QE. And all you have to do here is make PR the subject. So you see the thought process behind that, how I almost made it would have been a mistake because then I would have to like do it again. So you see the thought process. Just look at the way they put things and why would they put it like that, okay? Our reason for that is because of the proportionality theorem. Okay, and now we're just going to make PR the subject. How do you make PR the subject? By getting rid of PW. PW is in the denominator. Okay, it's saying divided by PW. So to get rid of it, you would multiply by PW. So times PW, but this is an equation, so what you do on one side, you must do on the other side. So therefore, here the PW's cancel, and so PR is equal to, and now we can just put that there. They wrote PW first, I'll put it first. PW multiplied by QR over QE, and there we go. Okay, moving on to the next question. Okay, in next question, 11.2.2 says, if, okay, this is a proof with reasons. Proof with reasons that if, okay, so they're saying proof with reasons that if you are given that triangle PQZ is similar to triangle RQP, then you need to prove this. So with this, you don't even need the diagram. In fact, if you use the diagram, I mean, you can use the diagram, but I would not because I wouldn't want to get intimidated by, the shape itself. I'm going to focus on this and the letters they have used. And then, of course, if there is a need for the diagram, I'll go back to it. Okay, it's only 1 mark. So with similarity, if triangles are similar, then their sides are in proportion. And here's how we can show them that their sides are in proportion. Because these two triangles are similar, this is what it means. It means that if you take this side, PQ, right? It's the first and the second letter. So in the next triangle, you need to also take the first and the second letter. So you're going to take PQ over RQ, right? That this is going to be equal to QZ over QP, which is equal to PZ over RP, and so on. But here, I don't want to take random things. I want to focus on what they used here. Since they have PQ squared, the only way we could have gotten PQ squared is if they had PQ times PQ. So I'm going to focus on taking PQ here in this triangle, which is PQ. So with PQ, naturally, I have to take it with the first and second letter as well, since this is the first and second letter. So that is with RQ. And then it is equal to, and then I also see that was PQ squared. So there was another PQ they used. Where did they get that PQ from? Clearly not from this triangle. We already took PQ. So they probably took it from the second triangle. There it is. QP, which is PQ. Okay, so I have to take QP or PQ, but the way you take it is important. You see that with this proportion, we took the first triangle's length over the second triangle's length. With this one, you have to do the same thing. First triangle's length. So what would be paired with QP here? Because we took the second and third letter, in this triangle, you must also go with the second and the third letter. So that is going to be QZ over, and then here, QP or PQ. I'll just call it PQ, following the order in which they named it. Okay, so first triangle over second, same thing. You have to say first triangle again over the second one. And that's how we pick those sides. So you can see they just cross multiplied. We can do this with fractions. So we have QP times QP or PQ. Why do I keep calling it QP? PQ squared is equal to, and then we multiply across as well. And we're going to get, and I just want to put it in the same order. It's RQ multiplied by QZ. And there we go. You've proven what they asked you to prove. Okay, so that's how we would work on that if we ever found that two triangles were similar. Moving on to the next question. Okay, now I feel like with this question, they're probably trying to lead to something like this. Okay, so yeah, just watch out for that. They want us to prove that two triangles are similar. So let's see these triangles, QSZ and QRS. Okay, so let's just highlight those triangles. We have QSZ, I mean, we don't need these anymore. So triangle QSZ is this triangle, and then triangle QRS is this triangle. Okay, so let's see why these are similar. So for triangles to be similar, there are two ways that you can prove this. It's either that their sides are already in proportion, then they are similar, but for the sides to be in proportion, you have to have the length of these sides. As you can see, they have not given us any numbers, okay? There's no angles, no sizes of the angles, and there are no lengths of the sides. So the second way is what we would have to use. You would have to prove that the corresponding angles are equal in these triangles. What I mean by that is if you have two triangles, to prove that these two triangles are similar, you have to show them that this angle is equal to this angle, and this angle is equal to this angle, and then this angle is equal to this angle, okay? So they have to be equal. Let's see how that happens. Okay, another easy way to do this, if you don't want to stress too much about it, you can focus on the way they have been named. Just know that they have named them properly already. So you can focus on the way they have been named. We can already see that angle Q2 is common. It's a shared angle in both triangles, okay, in this triangle and in the bigger triangle. So by default, that is already equal, meaning we just need to find one more angle in these two triangles that are equal. And then, of course, by default, the third angle will be equal, seeing that all the angles in a triangle must add up to 180 degrees. Okay, so I know for sure that this angle Q2, which is the Q that they have there, they are equal. So here's what I mean by following the order in which they were named. You see the S here in this purple triangle? I'm going to try to find out what they are referring to as S. You see that in this triangle, that is QSZ, right? That is angle S1. They're basically saying from the way they have named it, it means that angle S1 is actually equal to the angle R here. And what is angle R in the blue triangle? That will be this angle. And now we can just look at that and figure out why are these two angles equal? See, that's an easier way to do that. Focus on the way they've named it. If they've named it for you, that already makes it very simple to work with. Okay, so why are these two angles equal? From the way it already looks like a theorem we're very familiar with. This is a tangent, remember? This is a chord, okay? And we know that the angle between the tangent and the chord is equal to the angle at the circumference, which is subtended by that same chord, tan-chord theorem. Okay, so there we go. Okay, so that was very simple. Focusing on this gets you to that. And this is the first time I'm seeing this paper, because if you have to go through the paper before actually doing the video on it, you're going to take so long. Okay, so I will start off by introducing the triangles. We'll tell them in triangle, and we'll say this is QSZ and triangle QRS, and we're just going to state the things that are equal. Okay, we already have two angles equal, angle Q2 and angle Q2. It's a shared angle, so angle Q2 equals angle Q2, and we can just tell them this is a shared angle, so they are equal. The second angle equal would be this. Angle S1 is equal to angle R2. So we can tell them, and the reason for that was because of the tan-chord theorem. And so by default, the third angle is equal. Okay, so we can just tell them what is the third angle. That would be this angle over here, angle Z1, and this angle, this bigger angle here. Okay, that's the one we didn't speak about in the blue triangle. That larger angle. So I'll just go ahead and call it angle QSR. Okay, so we can tell them that angle Z1 is equal to angle QSR. And the reason is you can either say it's the third angle in the triangle, or because of the sum of interior angles, okay, of a triangle, sum of angles in a triangle. Okay, and there we go. We have three angles being equal. So finally, we can conclude that this means that triangle QSZ is indeed similar to triangle QRS, and that's because we have three corresponding equal angles. So we can just tell them because of angle, three angles being equal. And there we go. Moving on to the next question. Okay, the next question 11.2.4 says we need to prove that PQ equals QS. Okay, PQ and QS. Immediately they start saying two sides, you can already start thinking maybe it's a triangle, but we'll just see. Okay, PQ and QS. I'm just going to erase these triangles. We don't need them. However, we will probably need their angles, so leave those marked. Okay, so this is PQ and this is QS. So why are these two equal? Why would they be equal? You know how I wanted to use a triangle? Yeah, that's not possible here. I can't really say, oh, this is a triangle. That line is not even there. So we're going to have to think about this. Why would these two lines be equal? Now, this type of question, it feels weird because you're asking for two sides that are equal, but we're only given, we're not even given numerical angles. So how else could we do this? Whenever you are in doubt, just look back on what you already have. So all through, let's just look at what they were doing here because it would follow a specific trend. They are actually trying to follow a specific pattern. So it has something to do with what we already found. That's something we should know definitely. So what can we do with all this info? Okay, I already see something. We have PQ, right? We found PQ squared specifically. And it's one of the things they want us to find. They said, show that PQ equals QS. We know what PQ squared is. How about we focus on finding QS? And I can already see with the previous triangle, we can just use the previous triangle to do this. You see, there's QS. There's also QS there. We'll see if we need it or not. We can just try to find an expression for QS. So I'm going to just keep in mind that PQ squared was already equal to this. Okay, so I'm just going to put this down. This was already equal to this. And now let's find an expression for QS, possibly QS squared. Okay, so we can actually compare them. So QS, okay, I'm going to take this as the first and the second. So I have to take it with the first and the second letter. Okay, so QS over QR. And with this, it's not really guessing. What we're trying to show them is that they are equal. If we have PQ squared, then of course you can find QS squared and then compare it, right? But you can also focus on what PQ squared was equal to. It included an RQ and a QZ. So we can also just try to do that. So if we try to include RQ here, okay, that's QR, then you see that there's no use of doing that because we already took QS over QR. We already have that. So it means let's try to bring in a QZ. To do that, I take the first and the third letter, QZ. So it's going to be QZ. And so because you took the first and the third, it should also be the first and the third letter as well. So that is going to be over QS. Interesting. Okay. So once we put this down, these proportions are only true because we had similar triangles. So you can just tell them it's because these two triangles were already similar. So remember the first thing that I've just put down, I'm not stating anything. I'm just putting back what we already had. Okay, so I'm just remembering that we have this. But as we can already see, it definitely has a lot to do with what we're working with. So I will start by saying, since we already knew this, okay, this was proven from the previous questions, then this is what we are working with. And the only reason I can use these proportions is because these two triangles were similar. So that's my reason, because we had similar triangles. Okay, so now let's form QS squared and see what it's equal to. To form QS squared, we would have to cross multiply. So multiply here, that is QS times QS, which is QS squared. And then multiply here. You see that we have the same thing. This is an RQ. I mean, you can call it RQ just to make it look the same. So RQ times QZ. So that's RQ multiplied by QZ. Do you see how they are both equal to the same thing? Okay. So to make this better, what we could have done is just stated this first and then say, but do you see how PQ squared was already equal to RQ times QZ? Okay, so instead of saying it there. And this was proven. Okay, because they're both equal to the same thing, we can also just equate them. So I'm just going to go ahead and say, so this means that PQ squared is equal to QS squared. And of course, if you square root both hand sides, this means that PQ really is equal to QS like they asked for. Okay, so it seemed like the type of question where they're actually using these sides, but no, they were actually using a calculation we already previously found. Okay, so there we go. And that would be our answer there. That's how we would prove that. It was just by bringing back what we already knew here and then finding QS squared. Okay, so that is it for that question. And moving on to the next question. The last question, question 11.2.5. Yeah, I'm just going to go ahead and start highlighting. So let's pin this to the screen and then see which sides exactly they are referring to. It's interesting how they have a square root. These sides were squared. So if you had to find them, you would have to square root them. Okay, so already what I'm seeing here is they said we need to prove that PW equals QE times PZ over, but then they square root this. This is QR times QZ. Do we have that here? Yes, okay. QR times QZ is the length of together, of course, gives you QS squared and PQ squared. So they could have square rooted either one of those. We'll just see. So this could be it could be PQ or it could be QS. We'll see which one it is. Okay, so let's see in the diagram. Okay, so the sides that they're using, they have PW. So where's PW? That's over here. Interesting. That's one of the sides we used in the first question. And then they have QE. Okay, another side in the first question. And then PZ. Okay, so PZ is way over here. And then they also use, of course, this one in the denominator. It's between PQ and QS. We'll see, because they clearly square rooted that. Okay, what I mean by that is, remember how PQ squared was equal to QR multiplied by QZ? Then they probably square rooted both hand sides, and so therefore PQ is equal to the square root of QR times QZ. Same goes for QS. Okay, so they could have used either one of those sides. Let's see. So just to show that, I'll say they either used this or they used this. I don't know which one. We'll see. Okay, with this, I'm still looking for that PZ and where exactly they used it, because these two make sense. Okay, this and this, they're okay. We can actually see how they might have put that in, because from the way they wrote this as PW equals, and QE is here. If you wanted to move QE to this side, because it's currently in the numerator, when it moves over to the side, it will go to the denominator. And so that makes perfect sense. So PW, okay, goes over QE, like we can see here, okay. So that part we can probably still sort out. Okay, so if we were rewriting this, we can write it as PW over QE, okay, and then it's going to be equal to, we still have PR on this side. When you try to take the QR over, because it's in the numerator, it will go to the denominator. And so this would be equal to PR over QR. That's what we would have there. So I think the key to this would be to find out exactly where PZ appears so we can understand how they formed this. So with PZ, do we see any PZ anywhere? Okay, not in the actual equations that we formed, but it is in this triangle, in those two triangles being similar. There's PZ. It's the first and the third letter. So if we take PZ, you're going to have to take it over the first and the third letter here, RP. And then this would be equal to, and then, we can find out what it's equal to. Okay, so what could we pair this with? I would want to pair it with things that somehow relate to this, because I can see how they got the PW over QE. Okay, that part, the PW and the QE. But now with the PZ, let's try to pair it with something that has QR in it. So immediately in this triangle, what I'm going to immediately try to do is find that QR I was talking about, QR. So let's see, where would QR be here? It's in the second triangle. Here's QR. Okay, so because it's the first and second letter, you have to take it with the first and second letter. And so you have to take it as PQ because it's the first triangle over the second one. I started as PZ, first triangle, okay, over RP, second triangle. So I have to go PQ, okay, first triangle, over, and that's the first and second letter, so first and second letter, that is RQ. And let's just see, does that make any sense? Yes, okay, PR and QR is the same thing as RQ and RP that we have here. The only thing is that we have the RP here. So I can see the triangles they're using. We just have to now make sense of it. Okay, so let's just remove this and we're just going to start from here. So remember how they already told us that these two triangles were similar. Okay, so I'll hold this here and let's actually just start from the one that was more obvious, which was this part. Okay, so they started with this. Okay, so since they started from here, remember how we were able to prove this? I'm going to start from here. And I'm going to tell them, since you told us this, and I'm going to isolate that PW and that QE. Okay, so I'm going to start here since this is what we have. And now let's just take this apart step by step. So to isolate them, let's leave the PW and the QE. So the PW is in the numerator. I want to leave it in the numerator, and the QE is in the denominator, but it's on the side, but we'll see. Okay, so how we would do this is we can move this back so it ends up looking like this. It's like multiplying both hand sides of the equation by QE to get rid of it in the denominator. But you know what you do on the one side, you must do on the other side. So we have PR multiplied by QE is equal to, and PW multiplied by QR. And so what they did is they left PW on one side. Okay, so I'm going to leave this here. And so what it means is that QR needs to go. So to get rid of QR, because it's multiplying to PW, we would need to divide. So divide both hand sides by QR and QR. Okay, so that cancels here. And now what we have is PW is equal to, and it is just going to be QE multiplied by PR over QR. Okay, so this is since we already knew this, which was already proven. Okay, I'll just remove those now. So this was already proven. So now you can see the only thing missing for us to have what they have is to find out how they got PZ over this, square root of that. But we know that it's either PQ or QS. Okay, so we have the QE. And so what I said I'm going to use with that is this triangle. So I'm going to take these two triangles. Okay, so these are the triangles they said were similar. So I'm saying since these triangles were similar, this is what we can conclude from this. Okay, so this is what I want to conclude. I'm taking PZ over RP, and I can just do that again so you can see how we did that. We say PZ over, so if you take PZ, you have to take it with RP because it's the first and third, so first and third. So RP. So remember, it is this triangle's length over the second triangle's one. And then that is equal to, and then we took these, okay, PQ over RQ. So if you're taking PQ, PQ has to go with RQ, first and second letter. So PQ over RQ. Okay, so how can we get this to end up looking like that? So they have this PZ, and they've clearly put it over either PQ or QS. But you can see that in what we have here, what we have is PQ. We don't have the QS. So we're going to go with PQ here. I'm saying what they did was they got the PW, the QE, and then they said PZ over something. And that something now is the PQ. So let's see, how do we get PZ and PQ isolated? You're just going to do this by transposing. So when you see PR here, it is in a fraction. It's specifically in the denominator. When you transpose it, it goes to the numerator. So what happens is PR is now on this side in the numerator, right? And then what is still here? The PZ is still in the numerator. Then what else did we need to move? We want the QR to be in the denominator. So there's QR or RQ. Let's just call it QR. Do you see that it is already in the denominator? So I will not move it. I will leave it in the denominator. What else do we have to do? Do you see that the PQ is still here? I don't want it here. I don't want it to say times PQ. I want this gone. I want PR over QR. So I'm going to move this from where it is and transpose it. So it's in the numerator here. It will go to the denominator. And there we go. We have isolated this PR over QR. And so now, because of this, you can, of course, just rewrite it and tell them, I know that PR over QR is equal to PZ over PQ. And then this is going to start making sense. So now, with this info, we're going to take this that we had. And you see, if we substitute in place of PR over QR, we're just going to have that filled in. Okay, so we were able to get to this point. And so in place of PR over QR, we substitute PZ over PQ. If you like, you could have written this as PW is equal to QE multiplied by PR over QR. But because you can see that this is equal to this, therefore PW is actually equal to QE multiplied by PZ over PQ. Okay, so this is what we have. Now, the only thing left to do to get it to look like this, and let me just pin this. Okay, so you can see that the last step to get it to look like that is just to find that value of PQ. Okay, so this is what we have right now. Then you can just tell them, but we knew that PQ, okay, squared, and this is where we bring that back. PQ squared, remember what that was equal to? It was equal to RQ times QZ. We spoke about this initially because you saw that they used the same letters here. Okay, so I'll call it QR times QZ. Okay, RQ, QR, same thing. And so if you square root both hand sides, PQ is actually equal to the square root of QR times QZ. And now we're just going to put that in place of PQ. So finally, PW is equal to QE. And then in the numerator, these are multiplying times PZ all over the denominator of PQ, which is just the square root of QR times QZ. Okay, there's a shorter way to put that down, probably, but I was just trying to show this step by step so you can see what happened there. Okay, but that is it. That's how they got to this point. Okay, you see, they're just taking some equations that are already true, and then they're forming a new equation from this. And you just have to make those links by using the sides they've given you, or also just looking at things that you've already proven. It's always going to be like this, grade 12s. So yeah, just make sure you practice and keep practicing, keep using past exam papers. Those are really the type of exams that you can go through to really just prepare you. So November exams would be very helpful. Okay, so that is it for this question. And that wraps it up for the Euclidean geometry section of this paper, and really just this whole paper too. If you guys have any questions, or you guys actually work through some of these questions in a different way, feel free to comment in the comment section below, and I will see you guys in the future videos. Bye.